Hello learners, welcome again to our lesson 3 of the Form 2 chemistry. We are looking at the first topic of Form 2 chemistry, that is the structure of the atom and the periodic table. So today we are going to look at lesson 3. Previously we have looked at the structure of the atom. We looked at the first 20 elements of the periodic table, the groups and the periods in a periodic table, and today we are going now to look at something else. So we are going to define two terms. One is the isotopes and another term, the relative atomic mass. So we are going to start by looking at what are isotopes. So the definition of isotopes is as follows. Isotopes, these are atoms of the same element that have the same atomic number, or the number of protons are the same but different mass number, or different number of neutrons. So isotopes, these are atoms of the same element that have the same atomic number but different mass number. We have a table here that gives two elements with the isotopes, the examples of the isotopes here. So the first element is hydrogen. Hydrogen has 3 isotopes, you can see there. Then carbon has 2 isotopes, that is 1, carbon 12 and carbon 14. Those are 2 isotopes of carbon. So that is what we refer to when we talk about isotopes. In our next slide, we are going to look at the relative atomic mass. It is usually abbreviated as R.A.M. So what is relative atomic mass? Relative atomic mass is the average mass of an atom compared to 1/12 of the mass of an atom, of one atom of carbon. So that is the definition of relative atomic mass, the average mass of an atom compared to 1/12 of the mass of an atom of carbon. So we calculate the relative atomic mass in comparison to 1/12 of the mass of one atom of carbon. The instrument used to measure the relative atomic mass of elements is known as the mass spectrometer. That is the instrument used to measure the R.A.M. of elements. The relative atomic mass is closest in value to the most abundant isotope of the element. So, if we have two isotopes, one with mass number 20, the other one with mass number 23, for example, and the relative atomic mass of that element is 20.1, then definitely the most abundant isotope will be the isotope with mass number 20. So this is what we are saying, the relative atomic mass is closest, is the one close to the most abundant isotope of that element. The relative atomic mass has no units, so never put units when you are asked to calculate the relative atomic mass of an element. So now we are going to look at a few examples on how we calculate the relative atomic mass of elements. So for the first example, we are looking at chlorine. We have chlorine. Chlorine 35 forms 75% of the mass of chlorine, and chlorine 37 forms 25%. Calculate the relative atomic mass of chlorine. So now here, to calculate the relative atomic mass, we say relative atomic mass is equals to what? Mass number of the first isotope multiplied by its percentage divided by the total percentage, that is 100, that is 75 plus 25, then plus the mass number of the second isotope multiplied by its percentage divided by the total percentage, which is 100. So for the first isotope, its mass number is 35. So we shall have 35 multiplied by its percentage is 75 divided by 100. Then we add the mass number of the second isotope is 37 multiplied by its percentage is 25 divided by total percentage, which is 100. So when we multiply this one, we are getting the first one is 26.25. I've calculated mine, 0.25. The second one is giving us 9.25. So the relative atomic mass becomes 35.5. So that is the relative atomic mass of chlorine. That is how we calculate the relative atomic mass. We look at the second example. So we have example 2. Determine the relative atomic mass of an isotope of element C with the following mass number and relative abundance. So we have mass number on that side. There are 3 isotopes with their respective relative abundance on this other column here. So whatever we did in this first example, we do it here. So let us multiply the mass number times the relative abundance. So we shall be multiplying 39 multiplied by 83.1. That is its relative abundance divided by the total percentage, that is 100, plus the second isotope has a mass number of 40 multiplied by its relative abundance, which is 0.01% divided by total percentage, which is 100. Again, plus the third isotope has a mass number of 41 multiplied by 16.89 divided by 100. So when we multiply and add all this, the answer will be 39.3379. That is the relative atomic mass of that element C. We move to the next example, that is example 3. Element K has 2 isotopes with mass number 16 and 18 in the ratio 1:3 respectively. We are told to determine the relative atomic mass of K. So now here we are dealing with the ratios. So we have 2 isotopes, one with mass number 16 and the other one is 18. So their respective ratios is 1:3, meaning the ratio of the isotope with mass number 16 is 1 and that of mass number 18 is 3. So here, to get the relative atomic mass, we are going to take the mass number of the first isotope multiplied by its ratio divided by the total ratio, then plus the mass number of the second isotope times its ratio divided by the total ratio. So the first isotope has a mass number of 16, sorry. So we have 16 multiplied by its ratio is 1 divided by the total ratio is 1 plus 3, that is 4, then plus the second isotope has a mass number of 18, that's right, 18. So we are multiplying 18 multiplied by its ratio, which is 3, divided by the total ratio, which is 4. So when we multiply 16 times 1 over 4, that is 4, plus 18 times 3 over 4, the answer will be 17, 17.5. We leave it like that without the units. So the relative atomic mass of K will be 17.5. I hope you are following. We move to the next example, that is example 4. Now this one is using fractions. So we have element P consists of 3 over 4 of one of its isotope is X with atomic number 12, and 12 should be the superscript, so please note that, and a quarter of isotope X with mass number 14. So X12 and X14 are the two isotopes of element P. So we are taught to calculate the relative atomic mass of P. So we are going to say relative atomic mass is equals to, we take the first isotope, it has a mass number of 12. We multiply by its fraction, which is 3 over 4. Then divide by the total fraction, 3/4 plus a quarter, that one gives us 1. Then plus the mass number of the second isotope is 14, multiplied by a quarter, multiply by a quarter, this is a quarter, 1 over 4, then divide by the total fraction, 3 over 4 plus 1 over 4, 1. So the answer here will be equal to 12.5. This is the relative atomic mass of element P. We move on. So now we are going to calculate the percentage abundance. So in this example, we have lithium has two isotopes, that is one with mass number 6 and mass number 7. If the relative atomic mass of lithium is 6.94, we are told to determine the percentage abundance of each isotope. So we don't know the percentage abundance of each of them. But we know the relative atomic mass is equals to the mass number of the first isotope times its percentage divided by the total percentage, which is 100, plus the mass number of the second isotope times its percentage divided by the total percentage. So we don't know both the percentage of the two isotopes, but we know the total is 100. So if we take the first isotope 6 to have a percentage of relative abundance of X, meaning that with mass number of 7 will have 100 minus X. So we get the value of X. So we have 6.94 is equals to 6 multiplied by X over 100 plus 7 multiplied by 100 minus x divided by 100. So we have 6.94. The denominator is the same for the two fractions. So this would be 6x minus 700. We open that bracket, 7 times 100. Then minus 7 times minus x will be 7x. So divide by 100. So here we are going to get the value of x will be 6x minus x, that is minus x, will be equal to 6.94 times 100, that is 694. Then we have 700 there. So we are going to take now 694 to the other side. So minus x will be equal to 700 minus 694. So x will be equal to 700 minus 694, which is x would be 6. So x will be 6. So if x will be 6, then the relative abundance of 7 will be 100 minus 6, which is 94. So the first isotope will have a relative abundance of 6%, while that with mass number 7 will have a percentage of 94%. So this is with the mass number 7. So that is how we calculate the relative abundance or the percentage abundance of these isotopes. We look at the next example. An element X has relative atomic mass of 40.2. It has two isotopes of 39 masses, 39 and 42. Calculate the relative abundance of each isotope. We repeat the same procedure. So we don't know the percentage abundance, so we can let that of 39 be X, that with mass number 42 be 100 minus X. So we are going to take the mass number of the first isotope, that is 39, multiply by its percentage or its relative abundance, which is X percent. So 39 times X divided by the total percentage, which is 100, then plus the second isotope is 42, multiplied by its percentage abundance, which is 100 minus X over 100. So we have 39X plus 4200 minus 42X. So we have 39X plus 4200 minus 42x over 100. So this one should give us a relative atomic mass of 40.2. So when we calculate the value of x here, we are going to get that x is equals to 60. So if x is 60, meaning 100 minus x will be 100 minus 60, which is 40. So the percentage abundance or the relative abundance of the isotope with the mass number 39 would be 60%. And that one with mass number of 42% will be 40%. We look at the next example, example 3 here. We have an element Q. It has an atomic number 10. It has a relative mass of 20.2 and consists of two isotopes of mass number 20 and 22. So we are being asked, what is the mass number of the most or the more abundant isotope of Q? So previously we said that the relative atomic mass is closest to the mass number. So if we have the relative atomic mass to be 20.2, the isotope that is closest to the relative atomic mass is the isotope with mass number 20. So the mass number of the most abundant isotope is the one with mass number 20. Then B of that one, you calculate the relative abundance of each isotope, which of the two isotopes. So calculate the relative abundance of those isotopes. So the last example we are going to look at is example 4. We have element T consists of 3 isotopes, and the first isotope has mass number of 62, the second one has of mass number of 64, and the third one has mass number of 65. They are in the ratio of 7:x:y respectively. Given that the total ratio is 10, calculate the value of x and y if the relative atomic mass of T is 62.5. So let us calculate the values of x and y using the relative atomic mass. So we have the relative atomic mass is 62.5. So we should get 62.5 from multiplying the mass number times the ratios. So we have 62 multiplied by the ratio that is corresponding to that isotope, that is 7, then over the total ratio, which is 10, then plus the second isotope has mass number of 64. We are going to multiply by what? So we have the total ratios is 10. So 7 plus x plus y should give us 10. So x plus y should give us 10 minus 7, which is 3. So x plus y should be equal to what? To 3. So if you want to get what is x, we can say that x is equals to 3 minus y. So the ratio of isotope with mass number 64 was x, and x is 3 minus y. So here we are going to multiply by 3 minus y, then divide by the total ratio, which is 10, plus what? The third isotope has mass number of 65 multiplied by its ratio is y, then divide by what? Divide by the total ratio, which is 10. So we can move this on here. We can clear this part. We have seen how we are getting those ratios. So we can erase that part. So this will be plus that one. So here we have 65 times y, which over 10. Then we can clear this part here like that. So now we are going to find the value of y. So we just multiply here, open these brackets. So 62 times 5 times 7 is going to give us, we are going to get the value of the first one is 62 times 7 over 10 plus 64 times 3, then 64 times y, so that will be minus 64y, then 65y over 10. So after calculating this one, you are going to get the value of y. So y will be -1. So if y is -1, and we said that x plus y should give us 3. So what is x? So we have y is 1, so x plus y, which is -1, should give us 3. So x, we take -1 to the other side, we get 4. So x is 4. Then the ratio now will be 7 is to x. X is 3 is to ratio 4. Sorry, x is not 3, x is 4. So x is 4. So 7 is to 4 is to what? -1, which is y. So we were finding the values of x and y. So x is 4 and y is -1. So that is how we approach that question, and that is how we calculate the relative atomic mass using the percentage, abundance, and also the ratios and also the fractions. So that marks the end of our lesson 3. Till the next lesson, goodbye.